Right, hello. This is the video for lesson 2, dealing with binary and converting ASCII text to binary. I am doing this from the hospital because I have not let Ben go yet. So this is the best I can do because I can't be with you on Google Meets. So let's get started. All right, so we're going to show on this device. Okay, you can go back up. All right, so one thing that you definitely need to know is that everything goes back to binary. There will be a test question that will ask why do computers use binary, and it's because, remember, the make and model. You may have a Mac, you may have a PC, you may have a Apple device, or you may have an Android, but they all have to converse and send messages over the same network. So there's that protocol that uses the binary system to convert everything to bits and bytes and then sends it over the network, converts it back. Here, the second point is the larger the number of bits, the more numbers that you can use. You'll notice that I've talked to you before about this, that each column represents a bit. So you have here 8 bits, and if you go and add up all the numbers together, remember the highest number that you can have is 255. So that is the largest number you can transmit is 255. If you only had 4 bits, the highest number that you can send is 15, because you would add up the 8, 4, 2, and 1. Okay, so here's some sample questions I know that you would see on your unit test and on the AP exam. The first one is, what is the 4-bit binary number for the decimal number 12? This one you should be able to do already, and it is 1100. The second question, what is the minimum number of bits that you would need to encode a sentence with a combination of 26 letters? Well, that's easy. What you would do is go up to the highest number, because you only need to have 26 characters. You go up to the highest number that you would go to without going over, and that would be 16, and then use those because that would cover all 26. So that would be 5 bits, because that would be the 1, 2, 4, 8, and 16. Adding them together, that gives you 31. That will give you enough space, enough coverage. The last question I know you will see on the unit test, what happens to the highest possible number that can be represented in the number of bits when you add one more bit? This is an important concept to know. An example here is going from a 3-bit to a 4-bit. It doubles. If you look up here at your number line, when you jump up a bit, it increases, it multiplies it by 2. So it's very important that you understand that concept. And here's one more. 8 bits equals 256 numbers. Remember, the 0 also counts as a number. So it's actually 255 plus the 0, which gives you 256. This is a simple question I have seen. Our school keeps a database of students with each student's unique lunch number stored as an 8-bit number. Every possible 8-bit number has been assigned to a student. Before the incoming freshman can be assigned a new lunch ID number, what can the school do to ensure that the numbers are available? Because they're not going to get rid of students, I can tell you that. Well, the answer is add a bit. Going from 8 bits to 9 bits, if you take the 128 and you multiply that by 2, let me go do that right quick. 128 multiplied by 2, that's going to give you 256. So that would give you that would double the amount. So that would cover enough students when they come in brand new. All right. Here's a few more. If a student, I'm sorry, I cannot read. If 6 bits represent 64 different numbers, remember that the 0 counts as a number. How many bits do you need to represent twice that many? So if 6 bits equals 64, 64 twice is 7 bits, which would increase it to 128. And finally right here, how many more values can the numbers, values or numbers can be represented in an 8-bit message than a 4-bit message? And the hint, take the difference between the 4 and the 8 and then go to the chart. So that means subtract 4 from 8, which gives you 4. Go to the chart and you'll go up to the line with the 2's. You find the 2 to the 4. It gives you this, 16. You'll see a question like that. So you do the math, subtract 8 from 4. I'm sorry, opposite, 4 from 8, and put it over the 2. Go find that number in the chart and go down. Now that was just a series of review questions. All right, here's one more. So a video streaming website uses 32-bit integers to count the number of times each video has been played. In anticipation of some videos being played more times than can be represented with 32 bits, the website is planning to change to 64-bit integers for the counter. Which of the following best describes the result of using 64-bit integers instead of 32-bit? Well, again, you are going to look at the difference. 64 and 32, they just doubled it. They went up and they doubled it. So here's your answer. Here's a multiple choice. Is it A, 2 times as many can be represented? B, 32 times as many can be represented? C, 2 to the 32nd times can be represented? Or D, 32 to the second? I can tell you it's not going to be D because it's going to be base 2. Your answer is C, 2 to the 32nd. Again, just like in the other question, when you have something like this, you subtract the smaller bit from the bigger bit and you put it over a 2, and there's your answer. Okay, so now we have to focus on what happens when you're sending a text message. How does your device handle that? When you see letters on the screen here, when I was making this presentation, the computer does not know the letters. It only sees things in binary, but it has to convert it and put it on the screen for me and for you to read. So how does that work? Well, we got a couple of things here. Here's some Morse code. Morse code was actually the very first type of binary, because you have your ones and your ons and your offs, and we practice this with the SOS signals, and you would have there's states where either on or off. You either heard the tone or you didn't. And here's an example. So you can see here every letter has a representation, just like every number has a representation in binary. Baudit code came in after Morse code in the 1870s, and this actually used a 5-bit code, so that would equal up to 32 different symbols. And so it would transmit the Roman alphabet and use punctuations. And it was encoded with only 5 keys. That was pretty cool. And you can see here the tape at the lower right-hand corner. This is what it looked like. So again, it represented binary code. Now, let's talk about ASCII text. This was developed in the 1960s, even before I was born, and it was originally set up for a 7-bit numbering system. Remember, our bytes, our full byte goes for 8 bits. So the first 32 characters that were listed here, you can see here on the right-hand side, were basically about control. Things that we don't really use anymore because you have null, start header, device controls, and all that stuff. We don't really even use this anymore. So if you go over to the next lines, you can see here 32, that represents your space. That's like hitting the space bar. That gives you a 30, when you hit it, it gives the code 32, which the computer automatically converts to binary and calculates the 32. That's what the computer sees. And then if you go on down, you'll notice that every symbol is assigned a number. Every number itself is assigned a number. And then you will get to the letters. And you'll notice that there is a capital letter and a lowercase version. The capital letter actually is assigned, the capital letter A, I'm looking, is assigned a 65 in decimal. A lowercase a is assigned a 97 in decimal. So what you would do in order to convert ASCII to binary, you have to look at the letter, find the decimal number, then take that decimal number, convert it to binary, and then go back and forth. Okay, so again, all numbers, all 26 letters of our alphabet, capital and then lowercase, and then common punctuation symbols, have been assigned a number. Even the delete key. The delete key is assigned the number 127. Now, over time, the 8 bits became the standard chunk size for the byte. So all they did was add a 0 to the front of those numbers. So again, here it is up close that you can see. You should be able to access this as well on your screen for your activity that you'll do today. And I'm going to skip over Unicode. So, what you're going to have to do, you will be given an activity, and you are going to have to take the assigned number for the symbol, just like I said. You're going to have to go find the decimal number that is assigned to it, and then convert that to binary. And then you would have, and then if I give you the binary code, you will have to take that, convert it to decimal, and then go over and find the letter that goes with it. And if you remember IST, we did this. I know if you had me for IST, we did this. I'm pretty sure you did it with Miss Lennon or Mr. Howard as well. Okay, so let's go and look at what you got to do. Let's see here. I'm going to go pull it up. So right here, I gotta turn this on. Sorry, I'm doing this at the hospital, so it's a little different. There is the chart, so you can click here to open the chart. But this is what the file looks like. And so you are going to take the word car, go find the chart, and you're going to convert it to binary. So this one's pretty simple. So again, go back. Here we go. I'd open the chart. It takes a minute. I gave you this chart. So you go and find the lowercase c. It is a 99. Okay, so you can even cheat a little bit. This also has the binary code there for you. So you can copy that in back over here. Now, so you've got to do car, chip, truck, gas, home, and work. Then this is where it gets a little interesting. Be very careful because you'll notice that there are gaps in between this. So they're in groups of 8. So especially at item number 10. Now that is a little bit harder to read, but you can do this without cheating. Okay? So once you've got this done, you're going to submit and turn it in. I will have my cell phone. I've been checking my email, going in, and I'm grading here from the hospital as well because I'm looking at the same 4 walls and walking the same halls. So I'm watching what you're doing. So if you got questions, please let me know.